So good afternoon. May I go? Yes. Good afternoon to everyone and welcome to the last webinar of this series organized within the Accelerate project. My name is Barbara Merson and I'm a project manager at OGS, the Italian National Institute of Oceanography and Applied Geophysics. And today I will share this webinar on multidisciplinary laboratories for CO₂ geological storage monitoring. First of all, let me ask all participants to have the microphones and the camera switch off. I would also remind you that questions are very welcome. And you can write them in the tab you should see on the right of your screen. Questions will be answered at the end of both presentations in our panel session. Please specify to which speaker the question is addressed so we can simplify it. Finally, I remind you that this webinar will be recorded and uploaded on the ECCSEL YouTube channel. Before starting with the presentation, let me spend a few minutes about ECCSEL ERIC. ECCSEL stands for European Carbon Dioxide Capture and Storage Laboratory Infrastructure and is an ERIC consortium of 5 countries, namely Norway, France, Italy, United Kingdom and the Netherlands, grouping 28 facility owners providing open access to more than 100 world-class research facilities. The goal is to fight global warming and reduce CO₂ emissions in the atmosphere by exchanging the knowledge about CCUS, so carbon capture, utilization and storage, and has many goals. The ECCSEL ERIC consortium coordinates the Accelerate project, which started in 2020 and was funded by the European Union and has many goals. For instance, to increase the use and long-term sustainable operation of the infrastructure within the ECCSEL ERIC, but also develop marketing, access and services models for industry and SME, increasing the international collaborations and expanding the national nodes, and also extend the CCS to CCUS to include the utilization and also to expand to an industry level. Within the Accelerate project, there is a capacity building program with many activities as this webinar, but also specific workshops, summer schools, and dedicated training courses. So coming to today's agenda, we are very glad to host today Philippe Pezard from Geosciences Montpellier in France, who will talk about SHAGAL, a shallow experimental site to study subsurface gas storage processes, and Michael Jordan from SINTEF in Norway will talk about experience from the Svelvik CO₂ field lab. So I will ask to Philippe to turn on your webcam and we will give you the floor. Thank you.
Okay, yeah. Hello, everybody. The pop-up came too early, so I was not able to turn on the video and camera. So I guess I should be able from there. Alors, l'écran 2.
Sharing, yeah.
Yep, and this. And let's see if you can see it. Can you? Uh-oh. So I'm sharing, but afficher. Voilà.
Yeah, that's it.
Perfect.
Okay. right, so I'm going to speak about this facility that was included as part of the ERIC consortium a few years ago, and based on the work that we've done in the context of several European FP7, FP8 programs. And this is a development of shallow depth CO2 storage hydrogeophysical monitoring site, which we called SHALOG for ERIC. SHAGAL, sorry, for ERIC. We gave it an acronym. So the site is located, as you can see on this beautiful picture, just along the coast between coastal lagoons and the Mediterranean. And that's about 10, sorry. About 10 kilometers from Montpellier and our university, which is extremely convenient. So we developed that site from a petrophysical point of view. That's our main background in Montpellier. It looks funny because I've got the presentation on the left-hand screen, and I'm on the camera on the right hand, so I'm going to be looking sideways all the time. Let's look at an injection of CO2 from a petrophysical point of view. So you have a rock matrix defined by porosity and connectivity between the pores and porosity. And let's say that we start with pure water in that porosity. Once you inject CO2, you will end up with the previous water, CO2, and a mixed phase due to dissolution of the CO2 over time. So that means that while the matrix parameters, porosity and connectivity, might have changed if there is any carbonate in the rock in particular, the gas saturation and the pure water saturation will change over time. So at least we are facing a four-order problem if we want to monitor what's going on in a reservoir, at least in the near field, over time in reaction to injection or in the longer term. So for that, we don't only need characterization method, but also methods to monitor the evolution of the reservoir during injection and later storage. Basically, we need to record geophysical observables like seismic, electrical, follow near and far field changes over time. That might be the pressure field or the stress field, and try to manage fluid sampling to follow fluid rock interactions due to the gas injection. And for that, the ideal objective would be to have a series of integrated downhole monitoring techniques that we can apply to the reservoir and also the cap rock right on top, to have a multi-physics view of the evolution of the reservoir. Why put all those techniques together? You might say that this was tried at Ketsin about 15 years ago, but there were several holes dedicated to several techniques, one for seismic, a couple for electrical, and so on. And then when you want to analyze the data jointly over time, then the data might not be recollected easily. So the idea is to join all MMV techniques in one single hole, so that the data come from the same point in space. That reduces the number of holes, so reduces cost, but also reduces the leaking problem, the leaking risks. So in all cases, for having an integrated dynamic view of the reservoir in reaction to CO2 injection, for minimizing the MMV cost and risk, this is a real advantage. So this is the overall goal that we've tried to pursue over the past 10 to 15 years. At this site, I don't know if you can see my mouse, about 10 kilometers from Montpellier on the beach, as the picture showed, and here in the field, a series of boreholes, all dedicated to different type of geophysical monitoring, waiting for one hole where we'll be able to deploy all those methods in one hole. The sedimentary column we know very well down to actually 100 meters, deeper even than this hole, which was the first one we ever drilled. And we discovered a couple of reservoirs. There's another one at about 38 meter depth, but at about 12 to 16 and 8, 9, 10 meters, there are two shallow reservoirs overlapped by clays and surrounded basically by clays. So this is where we've made experiments in the past. We have cored completely. You saw the previous hole, mag 1, second hole, mag 6, the one going much deeper. We've logged all that. We've logged the core. Also, this is resistivity. This is sonic velocities, the compressional waves. And here we have porosity with a few measurements made in the lab from unconsolidated sediments. So we have two slim reservoirs, a conglomerate one and a real thin one at 9 meters, and lots of sand near the surface. So let's see how that looks. So basically, the gray here is all the clay, so you can see that the reservoir are pretty well isolated. Here we're at the level of an unconformity. All of this is described in a groundwater paper by Lofi et al. From 2012. We actually started to develop that site in 2004, a long time ago. What's really interesting is the nature of the pore fluid that can be sampled at that site, and I'll come back on that. You can see that deep down we have pretty fresh water here, about 1 to 2 grams per liter, and that when we come close to surface, we have almost here seawater being 35 grams per liter. So we have almost pure seawater, and we're located about 100 meters from the shore. We've made lots of downhole measurements. We've made pumping tests, fluid sampling, evaluated porosity, and so we have a very good geological and petrophysical knowledge of the reservoir. So we've been able to use that reservoir and site at the opportunity of 3 FP 7 and 8 programs. The first one was Mustang, second one was Panacea, the third one was Trust, but there was no field experiment in the third one. And every time we've used a setup where we have an injection hole, downhole observatories for resistivity, for seismic. Here is electrical observatory. Here is an hydrological observatory. This is a hole for time-lapse logging, and this is a downhole monitoring instrument for electrical resistivity. So we've developed a little bit that site between Mustang and Panacea. adding surface lines for electrical and seismic monitoring. So in the following, I'll focus on some of the findings we had on electrical resistivity, following several experiments. First, in 2012, we did a nitrogen experiment because it's a neutral gas, and we're in a reducing environment where bacteria would love if we inject air and oxygen, so we avoided that. So we did first nitrogen injection, then started CO2 injection in 2013. So that was that was very small batches of CO2 that we injected at a very small pressure. We didn't want to. We didn't have any purpose to inject lots of CO2. So let's look at electrical results. You can see here that prior to injection, we have a red baseline, which is somewhere in the middle of all the curves. And over time, with the injection, the resistivity tends to increase with gas saturation increasing. And well, with time, and these are the dashed lines, the CO2 is dissolving into the pore fluid, and the overall resistivity is decreasing. So we have a very good knowledge of what's happening in the two reservoirs. This is the shallow one here. Here it's looking at the same thing, but over time with a downhole permanent observatory. And this image is from repeated time-lapse logging. And basically what you can see is that the resistivity difference, which is positive with the presence of gas, is vanishing over time, the CO2 dissolving into the pore water. Same here in somewhat a cruder manner, because the vertical resolution of logging tools is 10 centimeters, while here we have a meter scale description. So we wanted to cross-check different methods. So basically, this is a better view of the time-lapse logging methods. And definitely, you can see the gas appearing here with the positive resistivity difference. And 30 hours, 50 hours, 70 hours later, basically, you can see that the gas has vanished, dissolved into the pore fluid. What was really interesting after that experiment was our possibility from a West Bay completion, a completion by which you isolate different intervals in a hole and you sample fluid exactly from that aquifer. So here we're looking at 3 different levels, 8 meters, 14 meters, and 15. So let's look at 8 meters. So we have a given pH level from fluid sampling in the individual reservoirs before injection. The injection starts here, and you can see that the injection is accompanied at least at 8 meters, here in blue, by a drop in pH as expected, and over time the pH, this pH drop, this small batch of acidity is being dissolved and disappear. So we monitor the pH of the fluid at these 3 levels right after the injection, and then over time. And you can see that this is 120 days, so about 3 months, 4 months, and 5 months after the injection, there is a sudden drop again in pH. So while we're doing no injection at all, just monitoring. Well, that is coming from gases being expelled from these coastal lagoons. We know that there is methane and H2S. You can see here the iron pipe being corroded by H2S with this very black liquid after staying overnight between drilling phases. And CO2 also is being produced. So there is a natural production. of CO2 under the lagoons. It's mostly biogenic, shallow depths gas production. So in reaction to that, what did we do when we realized that we have basically a background noise in gas production? We went in 2 holes, 3 days in a row. Here you're looking at 2 holes. Sorry, 1 hole, 2 consecutive days. And we decided to log an induction tool 30 times in each hole. So here what you're looking at is the resistivity divided by the median of the 30 logs each day. Each day 30 logs. And you can see that in the clays, the measurement error is very small, but the measurement varies quite a bit when it comes to the shallow reservoir or the conglomerate at different levels. So this is coming from the fact that gases are passing by through the pore space of the site, and in order to try to understand how this works, we developed a small model which is published in one of my papers in IGJJC. It's based on Waxman-Smith with a variable gas saturation, water saturation. So this small model allows us to compute the gas saturation. You see here a scale from 0 to 20%. And you can see that we are in the low range, except in the reservoirs at 16 meters, where during the looking back at the nitrogen injection in 2012 and the CO2 injection, you can see the nitrogen remaining in the pore space over time, while the CO2 slowly dissolves in the pore water, as we saw previously. And the range never exceeds about 10–15% at the most at the time of injection. Same from observatories here, but now looking at the gas saturation over time. And you can see that it's not really constant. Right here, you can see changes in blue colors, and variations over time, and this is away from any injection. And that led us to try to look at transfers between the conglomerate reservoir at 15 meters and the shallower, thinner reservoir at 8–9 meters, depending on the hole. And what you're looking at here is a cross plot of gas saturation at 8 meters versus that at 16 meters in 2 different holes. And you can see that it's perfectly correlated. Actually, the 2 curves are anti-correlated whenever, let's see, this is a gas saturation at shallow depths, and this is at deeper depths. Of course, there is a little more. So every time there is a drop here, there is an increase at shallower depths and so on, showing the communications between the 2 reservoirs from R1 at about 16 meters here to R2 at shallower depths. So basically, this was extremely interesting in terms of the monitoring concept, where when you're monitoring anything, you have to do that versus some baseline. And the baseline cannot be time 0. It has to be chosen with great care in order to provide effective results. I could show you a lot more, but seismic measurements in particular, or fluid sampling from this Schlumberger West Bay. Oh, well, it's not Schlumberger anymore. It's West Bay system, which I was mentioning before, multi-parker system with individual sampling zones. So the site was used at the opportunity of a CCS school that we gave in 2015 as part of the Trust project, where we made a demo of all the techniques being deployed together. And this was after our different injection during the 3 different projects. So what's the future of Magellan? We're still monitoring regularly the pore fluid and deploying new techniques like NMR that we ran quite recently for porosity and permeability of the downhole structure. The plan now is waiting for funding from Horizon 2030, to which we applied last year and were ranked 2nd by the European Community. In that project, I have proposed to deploy in one hole a multi-physics downhole monitoring device, including pressure, temperature, SP, but also optical fibers for downhole seismic and temperature, downhole resistivity, and fluid sampling facilities. To me, this, coming back to the introduction of my presentation, this is really the future of downhole monitoring of CO2, if that ever happens, and that's between us. But I'm really looking forward for our project to be funded and to start in 2024. So in summary, what is SHAGAL? It's a fully characterized shallow experimental site for gas injection experiments. It's a site to test new downhole hydrogeophysical monitoring sensors, and it's a site to develop integrated and compare integrated multi-physics monitoring methods. Thank you very much.
Thank you, Philippe. And we will give now the floor to Michael. Just
take me out.
Yeah, play a little with the. Yeah. So, Michael, please, you can turn on your webcam and try to share. Perfect. We can see your screen. And you are real.
Yes.
Thank you.
Hello. My name is Michael Jordan. I'm working with SINTEF in Norway, and I'm going to talk about the experience from the Svelvik CO2 field lab. And the purpose behind this presentation is to give an overview about what the Svelvik field lab is for those that are not very familiar with it. To give an update what has happened last for those that have heard about it, and also to give an idea what can be done and what to expect when doing an experience, when doing an experiment at the Svelvik field lab site. Okay. Yeah. So the site is located here in the south of Norway, in the kind of Drammensfjord, about an hour south of Oslo. And we are here on a peninsula, so located in a sand quarry. The site was established or designed as a quantification lab to test and develop methods for the quantification of CO2, especially to quantify and distinguish between pressure and saturation. It was designed to allow fast and cost-efficient and also repeatable experiments. So we have here an injection well where we can inject a brine of CO2 in 65 meters depth. And when we inject a brine, this will only affect the pressure. When we inject CO2, then initially we will affect the pressure and saturation, but when we stop injecting, then the pressure goes down to the background level really quickly, and we only see the CO2 effect. So we can, in a way, independently vary pressure and saturation. So the injection well is surrounded by 4 monitoring wells, and they're all 100 meters deep. These monitoring wells, and here's a picture of those. They have a PVC casing in order not to influence any electrical measurements. They are heavily instrumented on the outside with fiber optic cables, DAS, DSS, and DTS, both dried and helical. We have 16 ERT electrodes in each well. We have pressure and temperature sensors at 65 meters depth in 3 of the 4 monitoring wells, and of course in the injection well, the packer. And we can do fluid sampling using those capillaries. We have, as I mentioned, a lot of fiber optics here. The fiber optics are arranged in a loop, so starting at the instrument cabin, going down in the first well, going to the next well, and so on. And we can combine them in different loops, as shown by this figure using this patch panel. So we can combine them as we want and as we like. In addition to the instrumentation to the fiber optic cables in the 4 monitoring wells, we also now have a fiber optic cable in the injection well down to 55 meters depth. So we also have 3 groundwater monitoring wells here, here, and here, quite shallow. And so we have divers installed in these wells, and it has proved to be quite good to have this, because we have fluctuations of the groundwater levels, which of course influences the kind of pressure that we measure downhole. And there, what we see is tides. For example, you see this here in the small fluctuations, but we also have quite large variations due to water level changes in the fjord, but mainly kind of local precipitation. Here, for example, is a jump of about ½ a meter in groundwater level due to some heavy snow and rain. So what happens at the site when we inject CO2? So you have seen this picture, and what is shown here are 2 vertical sections, one along section A, which is crossing the injection well, and the other one section B from well M3 to M2. And so what's shown here is the difference between kind of repeat and baseline. So the change of seismic velocity due to the presence of CO2. This image was taken during the C2 injection, so a couple of days after the C2 injection was started, and this image here was taken after the C2 injection had stopped. And what we see is, so the C2 is injected down here. We don't see any CO2 accumulation, but we see CO2 accumulation around well M3, so around here, below mud layer at 38 meters depth. And we also see that when we stop injecting CO2, the CO2 is still there, but it starts to migrate. If we look at also seismic data, but at a more 4D view of that, so for this we have installed a seismic source at 40 meters depth during an injection campaign. And I have 2 examples now. One is where the receiver is located so that the ray from source to receiver does not pass any CO2. And the second one is where it crosses the CO2 plume. These are seismic waveforms for the no CO2 case. This is a is a duration of 8 days, and we see these cyclic waveforms are extremely consistent and do not change over time. And we also see this when we look at the spectrum. When we look at the CO2 case, then we see that also in the first few days we see hardly any change in the waveform, but then we see suddenly quite a large drop in amplitude and also a change in the first arrival time, which is corresponding to the CO2 plume. If we look at the spectrum, we see basically the same behavior. So the order here is from so the red one is a baseline, and then so the temporal order is from light to dark. We see that well, initially there's just not much change, but then we can actually identify when the changes happen, and then suddenly we have a big drop of due to large attenuation. What we also see is we see very different things going on in different parts of the spectrum. So a lot of information included in the seismic data that we want to find out and want to see how we can extract this information for the quantification. This is another way of kind of looking at it. Now we're looking at horizontal rays where source and receiver are approximately at the same depth. And we have this is a kind of summary. It's it's derived from the spectra. It's basically the area underneath the spectrum, and so we have all of these for the different measurements plotted over time. This is a duration of 4 weeks, and for different depths, so 35, 38, 40, 43, and 45 meters. These two layers, so to speak, they correspond to the CO2 plume. And here we have the start of injection. This is the end of the injection. White color means so these are kind of normalized to the start of the injection as a baseline. So white color means there's no change in the attenuation. Bluish color means there is increased attenuation. And what we see here when we start at the bottom, we see a kind of moderate increase of attenuation, and that's due to the CO2 bubbles coming up. So it's very sensitive. Interestingly, we have then a layer where we don't see any significant increase or change in attenuation, and we think it's some sort of clay lens, but not a clay layer. So there's no delay of the CO2 getting past this from this layer to this layer, so that it happens at the same time. CO2 is then collecting here underneath the seal. The interesting thing is also that in the top part of the plume, it takes significantly longer, a few days, until the CO2 builds up there. But we also see that after the end of the injection, the CO2 disappears quite quickly. This is a comparison of electrical measurements equal M3. So this is the depth, this is the date, and these are the dates of the two measurements here. These correspond to the same images that you saw before, just with a different color scale. But we see that there's a good consistency of seeing higher resistivity at the depths where we see the CO2 plume at well M3. In order to see how sensitive our data are to the detection of small amounts of CO2, we also did an experiment where we had a source and receiver clamped into place on both sides of the injection point. And this happened at the very beginning of the injection, so no CO2 had been injected before. And what you see down here, this is the pressure, this is the time, and So the small blue dots, these are the pressure values, and the larger dots are the times of the measurements. For orientation, these are just a few minutes apart. If we look at and we use the first one as a baseline, so to compare. If we compare this first, so repeat to the baseline, this is before the injection, we have exactly the same pressure. So we see the same waveform, and we also see the same P-wave spectrum, S-wave spectrum. The P-wave spectrum is taken in this time window. The S-wave spectrum is taken in this time window. When we go to the next one, so the ejection has started here. We have a small increase in pressure. And what I should say, what happens there is when we start injecting, then it takes a while until the CO2 actually reaches the reservoir. What happens is that we have to displace the water in the injection tubing and underneath the packer until it reaches the screen. When we go further, it's about the same pressure. We see that so the S-wave spectrum is affected. We don't see anything change in the P-wave spectrum still. When we go further, then we have a significant increase in the pressure, but still no change in the P-wave spectrum. Some more changes in the S-wave spectrum. But then the next point, that's actually where the CO2 enters the reservoir. It's very small amount of CO2 yet. The injection rate was about 12 kilogram per hour. But for these few minutes, this is only a few grams. And we see a significant impact, so it's extremely sensitive to small amounts of CO2. What we have done in the past few experiments was looking at crossfall data, just because they have the highest signal-to-noise ratio and we have the best signal quality. And we have looked at it at different sections between the well. What we found out was that the CO2 collects somewhere around well M3 here. But what we didn't know was what happens actually to the north of well M3. So we this year we changed the topography to allow walk-away VSP line. We have conducted the experiments, and we had the first look at the data, and we see that the CO2 plume extends approximately the same area away from well M3, also in this direction. In addition to the CO2 plume, we can also see some leakage. When we inject CO2 here, so part of it collects as a CO2 plume, and about 10% of the injected CO2 ends up here on the outside of the injection casing. Here, this blue structure here is the injection, is the casing of the injection well, and this red structure here is an auxiliary casing going down 26 meters that was just put in place during drilling to avoid sand from falling into the hole, but it's not cemented or anything. So, and we know that and all the CO2 that's coming here out at the surface has to travel so between those two casings, at least the uppermost 26 meters. And we have looked into using that for kind of leakage monitoring. So the aims would be for detection of leakage and then the quantification of leakage. We have installed fiber optic cable down in the well, one part attached to the injection tubing and the other one just hanging freely in the well. We also have installed some hydrophones to compare conventional and dust data. In addition, we have installed a gas meter for the quantification of the leakage. Something very new that is a project that is just ending right now, which is a Merson feasibility study. Together with Geophysics, we've conducted a field experiment where the question was, can cosmic radiations and Mersons be used for CO2 monitoring? This is a it's based on a combination of muon detectors and the seismic data. The seismic data were acquired and analyzed by SINTEF. So the muon part was done by GeoOptic. So in order to do this, a string of muon detectors was installed in well M3 underneath the depths where we know that the CO₂ plume would form, and the reference the detector was installed in well M2. And these are first results showing the detection rates over the measurement duration, and we see a clearly increased rate due to the decreased density caused by the CO₂. To sum up, so the Svelvik Field Lab was designed for controlled testing of new technologies for CO₂ monitoring and well integrity. It allows fast and repeatable experiments. We have done so far 4 injections, and we see the same things happening every time. It allows independent variation of pressure and saturation. We have an extensive downhole instrumentation on the outside of the injection wells. The inside of injection wells is available for deployment of sensor technology, for example, muon sensors, but also seismic sources, receivers, or anything else that we can think of. We have an excellent seismic data quality and reproducibility, and as it's an excellent facility, there's open access. And I wanted to mention that there is this transnational access that is supported by the EU-funded project GeoInquire. The first GeoInquire call for transnational access will probably be out in January, and it will support costs necessary to perform the proposed research, so equipment, support of personnel at the installation, consumables, and training. And with this, I would like to thank all the projects that have helped us to conduct the experiments at the site. Well, thank you.
Thank you, Michael. And you can stay with us. And I ask Philippe to join with the webcam and the microphone.
Here we are.
Yeah, and as I said, you can write questions in the tab you find in the GoToWebinar, GoToMeeting panel. In the meanwhile, I had a question actually to both of you, but Michael just answered my question. That was if the infrastructure or your site laboratory is accessible, and which are the policy, I think through Excel, and if there are a possibility for students, this is my second question, to refer to you for thesis or traineeship. So maybe, yeah, you can both answer.
Yeah, if I start, so yes, the site is available. I think the easiest thing in terms of practical is to contact us directly. There's of course also the Excel site that can be used, and for the students, I would advise the same, just to contact us directly, and we're always happy to have students that would like to work with us, or that would like to work with the site or data from the site.
Okay, thank you.
So
and Philippe, your SHAGAL?
Yes, same for SHAGAL in Montpellier. Huh? It's definitely open access, and it can be used as a database for students. It's been used actually by several students that come just for one experiment, and benefit from the full petrophysical, geophysical, geological description of the site that we've accumulated over the years.
Okay, and in any case, on the ECCSEL website, you can find both facilities, and you can have the technical guidelines and to access and so on. Oh, yes, we got a question. Let me check. Okay, can those experiments be implemented for mega project, full scale injection?
Was it for me?
Chat?
There is not specified to which of you.
Can we see the question? Can we hear or see the question somewhere?
Yeah, the question appear on the. Yeah, the questions appear in a red question mark on your dashboard. In any case, I try to read again. Can those experiments be implemented for mega project? That means full-scale injection.
Yeah, maybe I can comment on that. What we see for this small-scale site on the seismic data, so we have seen that some of the effects that we have observed can also be seen on kind of large-scale data, both passive and active. But this is in a way two-step process. One is to do the experiments at the site, and then afterwards check if we can see the same thing on large scale. I think that these things belong together. So to check if the changes that you see, or if the effects on the data that you see is applicable to large scale site. That it works for some, we have seen that, but it may not work for all of them.
Okay, my point of view on that question is that over the years, initially only off-the-shelf technologies from the oil industry were used, just like at Sleipner with the 4D seismic, for example. So this was a viable technology. And the feeling of some of us, including me, is that dedicated technology has to be developed to address the question of knowing versus time, and at pretty high frequency, how is the reservoir evolving when you inject CO2? During injection and right after, or in between injection phases. And that technology does not exist. So the first step is to develop technologies, test them individually, eventually, as I said in my conclusion, group them together for question of risks, leaking risk and cost, and then apply them at greater depths. For the project for which we're waiting funding, the idea is to proceed with storage at 1500 meters, but in that project, I have proposed a test at 100 meters of all the technologies together. Because basically, when you look at the subsurface, the traditional way is to do logging, but logging is just a photograph one day in one hole, and you get a static photograph. The problem with questions like CO2 storage or gas storage in general is that we need the dynamic view. So we don't need the photograph anymore. We need the video. And this is what I'm after. Was that a good answer? At least understandable?
For me, yes. And for the participant too. So thank you. Thank you a lot. I don't know. I don't see any other question. Just let me check. No.
I have a comment. a small comment. A comment to Michael. It's very nice to hear about the development of the Svelvik site. You know, I was there in the field for at least 1 week when the site was constructed. That was a long time ago. And we had a lot of questions. We were injecting CO₂ and saw no answer until we discovered that there was a dip to the side, and it was coming out in a well 50 meters away. So it was a beautiful time to develop that site.
This first project that you just mentioned was very important for the kind of re-establishing of the site as it is now in 2019. I think this experience from this from the shallow injection then was quite vital to know what to do or what to try. Of course, you can never know before. But in this case, it worked out.
Yeah, it was called CO₂ Field Lab, and it was funded by Eurogea Plus at the time. That's quite a while ago, but you know, it was an exciting project, and I'm very happy to see that the site is very active with the muon and everything else. So congratulations to a colleague.
Well, thank you.
Okay. So thank you very much. As I said, this was the last webinar of this series, and it has been a great journey. We have got a lot of information about CCUS and interesting webinars on both the capture, transport, utilization, and storage. If you have missed some of them, you can find them on the ECCSEL webpage or on the ECCSEL YouTube channel. So I thank you, the speakers, and I wish you a nice evening, and thank you again for participating. Thank you very much. Bye.
Thank you.
Thank you.
Bye-bye.
Bye.